All right, so we are in week 2. This quarter is going to go fast. At least this class in this quarter is going to go fast because we've got lots of different stuff we're going to do, and it's just going to like pick up speed as we go. So hopefully that's a good thing. So what I want to do today is go over the ODP that you already finished and PA1 questions. And there's not an ODP due tomorrow morning, okay? So you didn't see one posted, that's the reason why. I will post one tomorrow morning, but it'll be based on stuff we're talking about today. So I wanted to give you a full 24 hours. So there's no ODP due tomorrow morning. But I want to talk about the ODP that was done Saturday in PA1 questions. And then I want to talk about memory. And I want to look at 2 ways of getting access to memory in a program. Static allocation, which is what we generally do when we make an array, integer x, bracket 100, and dynamic allocation, which is what we're going to do everything in this course after PA1. And this is going to be creating memory locations to use as the program is running instead of at compile time. And then I want to go into the gory details of C related to memory, the ampersand, the asterisk, a new thing, an arrow that you may have seen, and pointers and address dereferencing and all that good sort of stuff. And then tomorrow probably we'll use this and get started on looking at a new way to do linked list without having to have an array of struct nodes. And this will be a preamble to PA2. So before we jump into that, are there questions? And you can ask PA1 and ODP questions too.
Can we use G++ compiler in such dynamic memory access?
Can you use?
I mean, use the new and delete instead of Malloc and free.
So G++ instead of GCC?
Yeah.
I'd like you to stick to GCC.
Okay.
Yeah.
I remember you said if scanf accepts, so like for when you run the main program for PA1, you said if scanf accepts the input and stores it just to run with it.
Yeah.
So if, let's say, the user wants to print and they write the word print, scanf would still store the first character as P.
Yeah, so if you're using scanf, or if you're just switching on character 0 of the input and it's a P, if they say, you know, poopy, you can still go ahead and print. Right? I'm not super concerned about error checking, but I do want to make absolutely sure that if they just say I, that you don't go ahead and insert something. Or if they say I, haha, that you don't just go ahead and insert something. Those are definitely errors. So catch those. Same with search, delete. But yeah, if they type print, you can take that as a P. So 204, which was Friday's ODP, was this get first function. So this is not part of PA1 per se, except maybe for debugging, but it's working with this array of struct nodes as if it were a linked list. So get first takes a linked list, which is an array of struct nodes, and it's supposed to return the first data node, the node after the sentinel. Sentinel is always at index 0. So you're basically saying, is the node at index 0 pointing to another node? If it is, return that node's data value. If it's not, return a 0. And this error variable is an integer pointer that you set to indicate whether there was a node or not. So if the list was empty, you're going to set error to 1. If it's not empty, you're going to set it to 0. So here's here's some code to do that. So I'm using my null as -1. So there's two possibilities, right? If the list is empty, the sentinel's next field is my null. So remember, the sentinel, we're doing some dual interpretation of things here. Your linked list array data next valid. And when we say something like header equals 0 or current equals 2 or something like that, right? These are just integers, but we actually mean these are the indexes of the nodes in the array. So if we wanted to find the sentinel's next field, it's actually LL bracket the index, which is always 0.next. If we wanted to find current data value, it would be LL bracket current dot data. That makes sense? So to check the sentinel's next field, we check LL bracket 0.next. If that's my null, the list is empty, so we do two things. We set the error flag to 1, and we do that by saying star error equals 1, because error is a pointer. And we'll talk all sorts of pointers in a little bit. And then we return a 0, because it said return a 0 if the list is empty. Otherwise, LL0 is pointing to a node, and its index is LL bracket 0.next. So I actually saved that in a variable called index, and then I looked at that node's data value, which is LL bracket index.data, and I returned that after setting the error variable to a 0. So anything that functionally does the same thing in the end gets credit for that ODP. So questions on that? So how is PA1 coming?
I'll do the easy ones first.
Okay, good. You should definitely do the easier ones first. How many people have started PA1? Okay, good. How many people are fairly confident they can get most of PA1 to work by Friday? Awesome. Okay. Keep chugging on it. If you're getting stuck, let me know. Start a discussion, something. Something I wanted to point out. Our struct nodes have this valid field, which we initialize to 0 to say it's not in use. And when we put a node in use, we set that to 1. Make sure, as kind of a sanity check, that none of this code ever mentions the valid field, right? None of this should have to do anything with valid. The only time that valid matters is when you're looking for a new node, or you're trying to release a node because you deleted it and you want to make that space available in your array. And those things happen precisely in two spots, the get node function and the release node function. So those are the only things that should touch the valid field. And if your add function, for example, is manipulating valid, then you need to get some separation. That's this notion of an abstract data type, right? Your add function should not be directly thinking of this. It should be thinking of this block points to that block, points to that block, insert between here, change this pointer, and so on. It has to do things like, you know, LL bracket current dot data equals such and such. But it shouldn't know about the valid field. Okay, this will make perfect sense when we get to PA2. But that's just kind of a self-check that you can do. So add is probably the trickiest function to write, which some of you have already discovered. Print is probably the most straightforward, and it's also the most useful in terms of writing the others. So I would start with print, and then you got some choices. You can hardwire a list and then play with search and delete, or you can jump into add. But make sure you got a print working first, so you don't have to go crazy in GDB following pointers and stuff. And in knit, you've basically done it in ODP, so that's pretty straightforward. So no questions on this? All right. I'm hopeful. Yeah.
I'm a little confused, like, with the differences, like, my null, null, and, like, is that similar to a null terminator?
It's just a flag. So everywhere in your code, I want you to use my null.
Yeah.
And I want you to define it as a symbol that's equal to -1. But I'm using my null and null interchangeably when I'm writing pseudocode. It's basically a flag. And the idea is, if you're building a linked list, whatever your implementation looks like, whether it's a array of struct nodes or dynamic memory that we're going to work towards today, you've got to have some way to deal with the case where you're at the end of your list. Now, if this is an integer, which is the index of the next node, we've got to give it a special value to say there is no next node. Right? We could set a flag in here for end of list and just set that, but we don't want to do that. We want to use just these fields that we already have. So we just pick a value that we know is never going to be an index, and a convenient value is -1. But it's really just a flag, so I'm calling it null, or my null, because when we do dynamic memory, we're going to have the same problem. We're going to need a memory value that we know is not actually a memory value, but is a flag saying there's no node after this. And the value we use for that is 0, which is null. It's a symbol set up in standard I/O in ULL. Yeah?
So what should we define the null in the pointer to a struct?
For PA2, are you thinking?
Yeah, I think the
Null already exists.
Oh, so we will set a next to a.
You're going to set it to
struct
null.
node, right?
So, yeah, next is going to be a struct null pointer. I mean, a struct node pointer.
Yeah.
And at the end of the list, you're going to set it to uppercase NULL, null.
So what's that null mean?
Null is actually a pointer to a void, and its value is 0.
0.
And it's inside stdio.h. And for a long time, computers big computers have reserved memory location 0 as not actually a valid memory location. On a PIC processor, that's not the case. We can go to file register 0 and it's not a problem. But on most larger machines, if you try to access memory location 0, you get an error from the memory management system. And it's convenient because probably the most common thing you can have if you forget to set something with a particular value is that it's going to have the value 0. And so you catch a lot of errors if you simply avoid using memory location 0. And then if you've got something uninitialized and it tries to hit location 0, you get a seg fault instead of just processing random stuff. And it also lets us use 0 as this flag for not an actual value. It could be anything, though. You could reserve location -1 as unavailable, but usually it's 0. Does that help?
Yeah.
Okay. All right, so what we're doing in PA1, we have this array, and let me draw it a little neater. We have this array of structures. And throughout this, we've said this is going to be an array of 100 struct nodes. And so we can have 100 things in our linked list. We have a sentinel at location 0, and then we can have 99 genuine data nodes stored in our list. And when you write your main program, you've probably written something like this. Struct node LL bracket 100. And we played around with this a little bit in GDB last week, and we said wherever this array begins, if this is location, F800, and this is 12 bytes, then this will be location F80C, and the next one would be location F818, and the next one would be F824, and the next one would be F830, and so on. And each element of the array is just the next locations in memory after the previous element. Well, that works great as long as you know that you need 100 things in your linked list. But there's two problems. One, you might be having a day where you need to store 10,000 things in your linked list. And when you try to store the 100th thing, your getNode function is going to search. It's not going to find any space. It's going to say, sorry, we're out of space. It returns my null, and your code has to say, I can't add that 100th number. Or you might decide, okay, there's going to be some days where I need to store 1,000,000 things, and you're going to say struct node LL bracket 1,000,000. And there's two problems with that. There's three problems with that. One, 1,000,000 is a big number. So your program is going to be a memory hog. And maybe you're just dealing with linked lists of 10 things, but every time you run this, your system memory goes down to like 2% free because this linked list program is taking all the memory. Two, 1,000,000 might not be enough. There might be a day when you need 2,000,000. And three, we're requiring that all 1,000,000 locations in this linked list are sequential, because that's what arrays are. They're sequential memory locations. And so you're trying to allocate, if this is 1,000,000, 12,000,000 consecutive bytes in memory. And allocating 12,000,000 bytes is not necessarily that hard, but finding a chunk of memory where you have 12,000,000 bytes in a row that you can give to the user, that's a little more challenging. So this is what I'm calling static allocation. It's allocated in some sense by the compiler. You write your program, you say GCC, and when the executable is created, there's information in there which says when this program is getting ready to start, I need you to allocate 1,200 or 12,000,000 bytes of memory and call it LL.
If it doesn't find 12,000,000 consecutive bytes, would it just give an error, or would it move things around?
I think you'll get an error. I don't know. Let's try it. Ooh, that's weird. Did it actually do it though? Maybe it actually works. Okay. And I don't think that's just from this. Okay, good. So on a much bigger machine, this might work. But there's some kind of limit, and it's fairly small. Just because static allocation is limited.
The 1 million isn't a magic number, but it's somehow computed before the allocation. How does the compiler know how much to allocate?
It's gotta be, so you mean like integer x bracket size?
Yes.
That kind of thing? That's a whole different matter. That's later versions of C, and that's doing dynamic allocation, I believe. I think it's actually setting up the code to do a dynamic, like a Malloc or something. I've never actually done that in C just because it goes against my puritanical roots. So in the original versions of C, you had to have something here that resolved to an actual number at compile time. Modern versions of C, you can have a variable there. Other languages like Java, Python, you can have variables here, and that's all dynamic allocation. All right, so static allocation works well in limited situations, but what we're really looking for is how can we, at runtime, once the program is running, decide how much memory we want. And for most of our data structures, we're not going to use an array like this. This is useful for being able to play with linked lists, nodes, changing pointers, things like that, without getting into this detail of C, asterisks, ampersands, all that kind of stuff. But we're going to move away from this approach, and we're going to start working, since we have to allocate memory at runtime anyway, we're just going to build these structures out of pieces of memory that we get while the program is running. And so this is going to be the idea of dynamic allocation. And dynamic allocation can be as simple as this. If I say integer star x, I'm telling the compiler x is going to point to an integer, but I'm not telling it where that integer is. I'm saying x is the address of an integer, but I haven't told it what the address is. And in fact, it's probably 0 by default, or it's some random number. But whatever it is, it's a value that if I try to use, I'm going to have a problem. So x is a pointer to an integer. Let's take the thing that x points to and set it equal to 1, and then let's print out its value. All right, and that's almost guaranteed to give you a seg fault. So let's run it in the debugger. So the first thing we're going to do is take the thing pointed to by x and set it equal to 1. Let's print out the value of x, it's 0. And if I print the thing pointed to by x, it tells me I cannot access the memory location at address 0. That's that reserved location. So when I say, well, I don't care, I want to set the thing at location 0 to a 1, I get an error from the memory subsystem. That's a segmentation fault. So what value can I give to x? Well, one thing I could do is I could ask the compiler to set aside space for an integer called mynum, and I could say, let's set x equal to the address of mynum. And that's definitely going to work. So let's debug this. So I'm going to set x equal to the address of my num. Well, here's x right now. I think it already did it. Oh, no, it didn't. Okay, but for some reason x is not 0. But anyway, so x has no particular value to it. My num has the value 21,845. The address of my num is E57C. I'm about to set x equal to the address of my num. So if I execute that instruction, x is now E57C. And my num is still 21,845. If I set the thing pointed to by x equal to 1, it's going to change what's stored at this location, E57C, which is where my num is stored. So if I say star x equals 1, and I print my num has changed to 1. But more importantly, I didn't segfault because x was pointing somewhere reasonable. So what we're going to do when we build linked lists is every time we want to create a new node, we're going to have a pointer to a struct node, and we want it to point to some new location in memory. Right? In PA1, we want it to point to a new element in our array. In PA2, we're going to say, I want this struct node pointer, temp, current, previous, whatever I'm calling it, to point to a new piece of memory where I can store a struct node. And every time we get to that line of code and we say temp equals new node, we want it to point to a different location in memory where we can store a struct node. So this trick will not work for us in PA2 because if I do this, every time I set x equal to address my num, it's pointing to the same location. And if I do that 50 times, every one of my nodes that I set equal to the address of my num is going to point to the same block of memory. And all 50 nodes are going to be basically one node. So I've got to get a new address somewhere. And I could have, I1, I2, I3, and each time I want a new address, I could set it to I1, and then I2, and then I3. That's static allocation. We need dynamic allocation. And that's where our friend Malloc comes in. So Malloc is a system function whose sole purpose for being is to find a chunk of memory, mark it as being in use, and give us the address of it. It's exactly what your getNode function does. It finds a spot in your array that's not in use, marks it as in use, and gives you the address of that new block. That's what Malloc does. And Malloc takes one argument, which is an integer, which is the number of bytes that you want to allocate. And you include standard lib to set up Malloc. So let's get rid of my num. And instead of setting x equal to the address of some value, let's set x equal to Malloc. And I'm going to allocate 4 bytes because I know an integer takes 4 bytes today. That's weird. Don't forget your -G switch. Alright, so I'm going to call Malloc, right? Before I do this, x is equal to 0. After I do this, x is equal to some totally different looking address with a bunch of 5s in it. So 6260. If I look at what's stored at that location right now, it's a 0. I could also examine that location with an X command, and it's got a 0. But I'm about to execute this command, which says take the thing pointed to by X, set it equal to 1. So let's go ahead and execute that. And now if I print the thing pointed to by X, it's a 1. And if I examine that location, it's become a 1. Okay, so 6260, remember that. I cannot type. Oh, it's still 6260. Okay, that's my machine. I think if you do this on the actual Linux server, this number will come out different. There's no guarantee what this number is going to be. The only guarantee is this is going to be an address in memory where there is at least 4 bytes available. So let's do this. Let's throw this thing in a loop. So we'll malloc 4 bytes. We'll look at X, it's 56,260. We'll set star X equal to 1. And now we'll call malloc again. And now if we look at X, it's 6280. It's a different location. And we can go ahead and set that equal to 1, and we can call malloc again. And if we print X, now it's 62A0. So we're executing the same code. X equals malloc 4, star X equals 1, but each time we do that, this star X equals 1 is storing that 1 somewhere else in memory. So we've stored 3 copies of our variable 1 in this case at 3 different locations in memory. So if we examine that location in memory that we first got from malloc, it's got a 1. The next locations happen to be 0s. There's the second one that we stored. And the next 7 locations have whatever. And there's the third one that we stored down at 62A0. And this is probably where malloc would allocate another block. But we haven't done that yet. We haven't stored anything there. And debugger, you can say x/ and tell it how many times you want to do this. And so I'm examining 32 words in memory. And here it's a little easier to see where our ones are. All right, you got the idea so far what's going on? So let's get rid of magic numbers. Don't put magic numbers in your program. Because on this machine, an integer takes 4 bytes. On a PIC processor, an integer takes 2 bytes. On a processor from 2030, an integer will probably take 8 bytes or 16 bytes. So this 4 is a potential issue. But the compiler knows how many bytes an integer takes. That's part of the compiler's job. So there's a keyword we can use, size of. And I would like you for this class to make sure your argument to size of is a type of variable, not a variable itself. A type of a variable, int, char, double, struct node. So the type of variable we have is an int. So we're going to allocate size of parentheses int.
Is size of a function or an operator?
It's a keyword in the compiler. The compiler will replace this with number 4.
So do you need parentheses?
I think you do. Yeah.
If it's a number, still you need the parentheses or no?
If what's a number?
If after size of.
Size of should only take a variable type.
No,
Int, char, double,
Okay.
float, struct node.
Then the size, the one you take numbers, do they have like size? I saw some, it says size or zero. There is only size of.
Size of.
Okay. Maybe I missed
And in particular, don't ever try to use size of to get the size of an array. Sometimes it works, sometimes it doesn't. But if it works, it's probably not for the reason that you think it works. So I can do size of int. And everything's still fine. I don't know if you can do this in GDB though. Yeah, you can. GDB knows about size of. So I can do size of char. I can do size of double. What do you think size of a char star is? 1, 4. Any other votes?
Machine speed.
So what is a char star?
Pointer.
It's a pointer to a character. What is a pointer?
Address.
It's an address. So this should be what the size of an address is on this machine, which since it's a 64-bit machine, it's 8. If you run it on a 32-bit machine, it's 4. If you run it on a PIC processor, I have no idea what it would do. Probably not 4, maybe. If you run on an old Intel 8080, it would give you a 2, because addresses were 2 bytes. And if I did a double star, or I do an int star, it's all going to be the same, because it's just a pointer. Whatever you're pointing to, it's still an address. The size of the address doesn't matter. So here's a main function. I have an x, which is 100 elements. I have a function called myFun, which takes an array of integers and doesn't do anything with it. Alright, so I can print x. X is an array. If I print size of x, it correctly tells me it's 400. Because in my code, I said x is an array of 100 integers. The compiler knows an integer takes 4 bytes. It knows I've got 100 of them in x. It knows x is 400 bytes. Let's go into our function. So now I'm inside my function, and arg is that same array, right? Starts with a 2. But if I print the size of that, it's just 8. Exactly the same array. But in my function, All I know is that my argument is a pointer to an integer. So inside here, if I use size of arg, it's going to be 8. So the fact that size of in main will give me 400 is kind of a bug in some sense. That's why I say sometimes this will do the right thing, sometimes it won't, but not necessarily for the reasons you think. So I would avoid, just completely avoid ever saying size of x, size of arg, things like that. Don't use size of on variables. Okay, use size of on types of variables. So if I want to find the size of x in main, what do? 100 times size of int would be the correct way. So there's an integer. That's how big a single integer is. Go ahead and do some arithmetic. Multiply it by 100. If I want to dynamically allocate space for an array of 100 ints, use that as your malloc, 100 times size of int. And I hadn't planned to get into this detail today, but it came up anyway. Since everything we're doing in the rest of the PAs and the rest of the course is dynamic memory based, all the structures we're building, it's up to us to figure out where to store the pieces of those in memory. And one of the most common mistakes is I want to store a struct node somewhere in memory and I don't allocate enough space for it. Typically because I'm allocating a variable instead of a type. And so the system comes back and says, yeah, you can store your data starting right here, but it's only set aside 4 bytes. And I store my structure there. And then I want to store another thing, and I say allocate memory for that. Well, it thinks all of this memory is free, and it says, okay, you can store your thing right here. Well, that's part of the thing I already stored. And now my data is overwriting my data. And that's really hard to debug. So that's why I'm suggesting stick to size of variable type instead of variable, because it will spare you at least one path to pain and suffering. So what are we going to do with this? I'll get into this later. Let's see what we're going to do with this. So we're going to make linked lists. We're going to have a data node, and it's going to point to another node, and it's going to point to another node. And we're going to store some values in here, and it's going to be like the linked list we've been talking about for a week, and that we'll be talking about this week. Same structure, but the implementation is going to be different. Our nodes are going to be simpler. There's going to be a data piece, but the next field, instead of being an index to an array, it's got to somehow tell us where this next node is located. It's got to give us a way to find this next node so we can look at its data and its next node and so on. We're just going to store the address of this node in memory. So the next field is going to be a pointer. And what kind of thing is it supposed to point to? It's going to point to a struct node. So this is going to be a struct node star. So our node is simpler. It doesn't have a valid anymore. Our node is a structure having 2 pieces, a data piece, which is an int, and a next piece, which is a pointer to a struct node. And this is not self-referential because of that star there. If we said a struct node contained a struct node, the compiler will get upset. But we're not saying that a struct node is a piece of a struct node. We're saying there's a pointer. And remember, pointers don't really care what they're pointing to. For most cases, all we need to know is that this is going to be a memory address. But we tell it it's pointing to a struct node, so the compiler can tell us if we're doing something we shouldn't. Yeah?
Will be some are valid as well.
Don't need a valid anymore. Because we're going to get these things instead of from our own get node routine, we're going to call malloc. And any time that malloc gives us a memory address that's not null, we know that's a chunk of memory that we can store a struct node in.
Are you going to delete these memory allocations?
We're going to call a function called free. And free, you pass it the address of the node that you previously malloced, and it'll internally set the valid flag to 0. So it's doing what we used to do with the valid flags in the get node and the release node. So our node becomes a little simpler. It's got 2 pieces to it, but the second piece is the really cool one because it's a pointer to another struct node. And that should feel a little more like in harmony with this picture, because we've got a node, it's got a data piece, it's got a pointer to a node with a data piece and a pointer to a node. And what are we going to use for our magic value when we get to the end of the list? This magic symbol, uppercase null. So all the pseudocode that we wrote before is still going to work. The implementation of that pseudocode in C will be slightly different. When we want to get a new node, instead of calling our get node function, we're going to call malloc. And we're going to say malloc. And how many bytes? I don't know. I'm not a computer, but the computer knows. We need whatever the size of a struct node is. So this is a data type. If you type defed it, you could put the type def in here, uppercase node or whatever. But size of effectively struct node, this will come back and it'll give me probably 16. Maybe 12. Depends how it packs it. All right, so that's where we're heading with PA2, and like I say, the rest of the course we're going to be allocating memory dynamically. And if you say something like temp equals that, at some point we can say free, and we can free any value that we got from malloc, and it'll release that block. All right, so I'll spend first part of tomorrow going through more details on these aspects of C, the star and the ampersand, and this arrow notation. But I want to make sure we're all fairly comfortable with pointers and addresses of variables from here. So I want to just kind of refresh that, and then talk about this arrow, and then we'll start looking more at these dynamically allocated linked lists.